Last time I talked about asymptotic notation and how we can use the big O notation in particular to talk about the runtime of an algorithm or a piece of code program. Um, Let me very quickly remind you about that, and then we will see uh, uh, the time analysis of another algorithm that we talked about in the previous lectures. So the idea behind asymptotic asymptotic notation, and as I told you, there are a number of them: big O, big omega, little omega, and theta. But we only look at big O here. But the idea is that, first of all, if in the running time, the expression that represents the running time of an algorithm, if there are coefficients, we ignore them. So ignore constant coefficients. So if you have 3 times n, just treat that as 3, or 2.5 times n squared, just n squared, and so on. And the reason for this was that the coefficients in the running time depend on factors that change from one computer to another, one programming language to another, and so on. And we want this analysis to be applicable to uh, every implementation of the algorithm. So it's about the analysis of the algorithm, not a particular implementation in a programming language on a specific machine. So that's the first part. And then the second part was, if there are multiple terms in the expression added, only keep the one that is the most significant as n becomes larger. So only keep the most significant term when n approaches infinity. Okay, so that's like a technical term. It means that n increases without bound. And the idea in practice is very simple. So for example, if you have that the running time of your algorithm is 10 times n to the third plus 7 times n squared plus 231 times n, then first of all, you can drop all the constant coefficients. So you can say, I don't care about the 10, I don't care about the 7, I don't care about 231. So what's left is n cubed, n squared, and n. And between those, n cubed is the most significant one in terms of the growth as n becomes larger and larger. So that's the only one that we keep, and we say the running time is in big O of n cubed. And that's basically it, except that we are going to see more examples and elaborate on it a bit more. Um, but for the next example, what I have in mind is the linear search algorithm that we discussed in previous lectures. And if you remember, the idea is that you have a sequence, like an array of elements, and then a particular element that you want to see where that element occurs in the array, if anywhere, right? So linear search, and the implementation in C++ looks something like this as a function. So you have this function that returns an integer called that linear search, and the parameters are obviously the array itself. Again, we implemented this using templates, but in terms of the time analysis, it doesn't matter what the type of the array is, so I'm going to assume that it's an array of integers. Then we had the target, the element that we're looking for, which in this case is going to be an integer as well. And finally, we had the size of the array, and I'm going to represent that as n. Now, the idea is you start from the beginning of the array and compare the target value with the first element, second element, third element until you find it or you reach the end and you don't find it. In that case, you say the target value t doesn't occur in the array. So loop, I use the for loop, if you remember. So for I equals 0, I is less than the size, which is n, I plus plus. And then inside the for loop, we have an if statement that says compare t with the element at index I. So if t is equal to a at I, is an I, then what we do is we simply return the index because we have found the target. Otherwise, we go to the top of the loop and increase I by 1. So we go to the next element and compare it with t and so on. Now, if you get out of this loop without returning anything, then it means that we went all the way to the end of the array and we never find an element that matches t. So in that case, you say not found or return -1. So that's the C++ code for linear search. Now we want to see if we can find the running time of this algorithm. So again, starting from the inside, I have return I, or even better than that, the entire if statement. If you think about it, the time that it takes, if you forget about the loop and everything and only focus on the if statement itself, the time that it takes for this piece of code to do its task does not depend on the size of the array. You're just looking at the ith element in the array, and remember that we said that this doesn't depend on how small or large the array is. And then we compare it with another integer. Again, the comparison of two integers, that doesn't have anything to do with the size of the array in terms of the time. And then if it's equal, we're returning I, some other integer. Again, doesn't depend on the size of the array in terms of how long it takes. So this entire thing, we can say, can be done in constant time. And I'm going to call that C. Okay, now that we are done with the body of the loop, we look at the loop itself, and the number of iterations is n. The loop, if you think about it, starts from 0 to n minus 1, so it iterates n times, and every time it takes this much time, so we have to add those up. C plus C plus C plus C, that is n times C, or C times n. And then at the end, we have this return statement. Again, this doesn't take that much time. Actually, it's constant because, again, it doesn't care how small or large the array is, return -1 always. And it's going to be a different constant, most likely, and I call that C prime. So this is the time spent in the loop. Time spent in the loop. And then I have to add this C prime here, so the overall time, the time that it takes for linear search to do its job on an array of size n is the time spent in the loop plus the final return statement. Okay, now I want you to pause here and think about what we did. There is a small detail that is important, very important actually, that I left out intentionally. So I want you to think about the analysis that I did and find the mistake that I made in my analysis. My argument is valid mostly, but there is one piece of detail that I left out. So one more time, the argument is the if statement and the return, the time that it takes for this to be executed doesn't depend on how small or large the array is. There's some constancy, and then the outside return statement is another constant because it doesn't depend on n again, so C prime. And then the idea is that this if statement is repeated n times, so if you add the times C, 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 n times, you get C times n, so the overall time is Cn plus C prime. So what is the problem? Okay, if you think about it, the problem is uh, I said the iteration of the for loop is n times, but that's not exactly true because if we find the element that we are looking for in the second iteration or the fifth iteration or the 10th before reaching n, then we immediately return that. And if you remember from your knowledge of C++, you know that when you hit the return statement, the execution ends immediately. So if in the third iteration t is equal to a at 3 or 2, then we return that index and we are done. We don't go to the next iteration. So n iteration, I should say, at most n iteration. If you are unlucky and you have to do this over and over for all the elements, then you have n iterations. But if you find it earlier, then there will be less iterations. So here, instead of saying that time spent in the loop is equal to this, I should say time spent in the loop is less than or equal to t times n. And here we say again, t of n is less than or equal, right? In the worst case, it takes this much time, and the worst case is when t doesn't occur anywhere in A. In that case, you have to go through the n iterations of the for loop, and you don't find it, then you have to go through here, return -1, and that's the C prime at the end. But it is possible that you finish earlier than that. In that case, t of n is going to be less than this. But here's the interesting thing. This idea of being less than or equal to is also already built into the big O notation. So even though here we say that t of n is less than or equal to this, so first of all, remember that we don't care about the constant coefficient. So we have n and 1 here, and then between n and 1, n grows faster. So n is the final term that is left here. And I don't need to say t of n is less than or equal to big O of n. I can say equals. Okay, and that's because in the definition of big O, we say that this is an asymptotic upper bound for the running time. So it doesn't have to be equal. If it is less than or equal to, still, we say it's in the big O of n. So in the definition of big O, to wrap it up, there are three things hidden here. One is that this n, it could have been that there was some constant coefficient for this n that we dropped it, right? Remember that was the first thing about the big O notation. So it could be that this n was 7n or 10 times n or something. So that's one thing. The other thing is there could have been another term that were less significant than n, and we dropped that as well. And finally, when we say equals big O of n, it means that n is an upper bound. So it doesn't mean that it's equal to, it could be that the running time is less than or equal to that. Okay, so there you have it. That's the time analysis of linear search and then representing the running time using the big O notation. Okay, now the final example that I prepared for today is the other search algorithm that we saw in the previous videos, namely binary search. Okay, let me remind you how binary search works. So you have a sequence of elements, and let's say there are 9 values in the sequence. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. 9 values in the array. And this is from A, for example, and then you have a target T that you're looking for again. And the assumption for binary search is that the array is already stored. The input array is stored. Input array is sorted. Otherwise, binary search does not work. So it is sorted. So the numbers here are increasing like 2 and 7 and 15, 22, and so on. And we are looking for some specific number. Now, what we do in binary search, if you remember, is we find the middle index here, the element in the middle of the array. Let's say that's x, and we compare t with x. It's either that t and x are equal. In that case, the search is done. We return the index. Or it could be that the target value is less than the value in the middle of the array. And in that case, we say since the array is sorted, all the values in the second half are going to be even greater than x. So if t is less than x, then there is no way that t can occur in the second half. If it occurs, it must be in the first half. So what we do is we ignore the entire second half and we only focus on the first half. And by focus, what I mean is we make a recursive call. We call binary search again on the first half. And what happens is the same thing again. It finds the middle value, compares it with t, it's either equal, less than, or greater than x. Now, the final case is t, the target, is greater than the value. In that case, a similar argument tells us that we have to search the second half and drop the first half. So recursive call on the second half. Now, this is a recursive algorithm, and generally finding the running time of recursive algorithm requires a little bit of mathematical rigor. But I'm going to give you an informal explanation on how we can find the running time of this algorithm. Okay, so if you start with an array of size n, okay, so here n is 9. What happens is we either in the recursive call go to the first half or the second half, which means that the size of the array gets halved, more or less. Not exactly half because we have to remove the middle element first, so instead of n is n minus 1, and then it could be that n minus 1 is an odd number, so we have to round it up or down, but something in the neighborhood of n over 2 is the size of the array in the recursive call. And then the same thing happens in the recursive call. We divide it into two smaller arrays, so n over 2 becomes n over 4. And then n over 4 in the next recursive call becomes n over 8, and so on and so forth. So the question is, when does this end? And it ends in two cases. Either that your element is the middle element after one recursive call, two recursive call, or something. The target is equal to what you're looking at. So in the first call, t is equal to x. You don't make any recursive call. You just return 4. If not, and you have to search the first half, it could be that when you look at the middle value, t is equal to that, and then you don't make any recursive call. So that's one way that this chain of recursive calls can end. The other way is we keep dividing and dividing until we reach a base case when the size is 1. So asking how long it takes for binary search to finish its job is the same as asking if I divide n repeatedly over and over by 2, how many divisions it takes so that we get to 1. Okay, and this is a very simple mathematical question. Let me start by doing some examples first. So if we start with 16, then it becomes 8, then it becomes 4, then it becomes 2, and then 1, right? And you know that log base 2 of 16 is 4, which is the number of recursive calls that I have to make here. And similarly, if I start with 32, have 16 divided by 2 is 8, 8 divided by 2 is 4, then 4 divided by 2 is 2, and finally 1. So 5 steps, and we know that log 32 base 2 is also 5. So it seems like it has something to do with log base 2 of n, but just to make sure that we do this in a little bit more detail, so n over 2 becomes, I'm sorry, n becomes n over 2, that becomes n over 4, and then after y, it becomes n over 2 to the k, right? And we want to know when, for which k, this is close to 1, which is the same as saying n is almost equal to 2 to the k, which is the same as saying that k is log base 2 of n. Okay, so the running time of binary search is big O of log base 2 of n. Now, there are some details that I'm not talking about here for the sake of time, and also the level of this course. Again, in a course focusing only on algorithms, we will go through this in a little bit more detail. But one thing that is very important is, as I said at the beginning, this doesn't mean that when you call binary search on an array, you have to go through all these recursive calls. It could be that after 2 recursive calls, you find what you're looking for, and then you don't go to n over 8 or n over 16 and so on. So we should say that the running time is less than or equal to some constant times log n. But the good thing is that, as I said, the big O notation has that less than or equal to built into it. So what this means is T of n, the running time of binary search, is less than or equal to some constant times log n. What that constant is, as I said, depends on the programming language that you use to implement this idea, the machine that you run the code on, and all those details that we are not going to, or we don't want to even talk about, because we want to talk about the time analysis of the algorithm itself, independent from the programming language and the machine and the compiler. So that's the C. And then less than or equal to is because, as I said, it could be that you get lucky and in the first attempt, you find the target and you don't make any recursive call. Or in the second attempt, the target value is in the middle of the second half and you immediately find it. And again, you don't go through all of this log n recursive calls, right? So this is the worst case possible. And that's why we say T of n is less than or equal to C times log base 2 of n. But as I said, when you use big O, then you don't need to say less than or equal to, because that is built into the definition of the big O notation. Now, the final thing that I want to talk about here is that it's log n is much smaller than n. So for linear search, so first of all, we said that the running time is big O of n, right? And first of all, this is the worst case possible. When you go all the way to the end of the array and you don't find the element that you're looking for, then we're talking about some constant time n plus some other constant, right? So this is the worst case scenario, but there is a best case as well. And for linear search, if you think about it, the fastest incident that can happen that you find the target the fastest is when you start from the beginning of the array. We have it here, right? If when I is equal to 0, t is equal to a at 0, and then you immediately return 0 and you're done. So the loop iterates only once. In that case, the running time is just constant, right? And constant in big O notation is written as big O of 1. So constant time. So it is possible that linear search runs in constant time, but if that happens, then you're very lucky for that particular instance. So this is the best case, but the worst that can happen is big O of n. For binary search, we said that the worst case is order log base 2 of n. That's the worst case when you have to do all those recursive calls and reach the base case. The best case is in the first comparison, when you compare your target with the value in the middle, they match, and then you don't make any recursive calls. You say I found it at index 4 in this case, right? So the best case for the binary search is also constant time or order 1. So constant time. That's the best case. Now, usually we care more about the worst case. And For linear search, we have order n. For binary search, we have order log n. And know that log n, should know this from math, is much, much less than n. It grows much, much slower than n. And that means that binary search runs much, much faster than linear search. Now, if you think that, okay, if that's the case, why are we even talking about linear search? There is a point here, and that is, if you remember, linear search works on every array, but binary search works only when the input array is sorted. So it's faster, but it has this extra condition. So if your array is not sorted, then you cannot apply binary search. And in that case, linear search is your choice. But if it is sorted, then there is no point applying linear search because it's much, much slower. It takes much, much more time for linear search to find the, the value. And in that case, binary search is the right choice. Now, speaking of sorting algorithms, sorting here, that's what we are going to cover in the next lectures, and where we will see a few sorting algorithms and their running.